Today we're going to talk about applications of the rational and meromorphic asymptotics that we covered in the last lecture. This lecture is really a turning point in our study of analytic combinatorics. We've been doing quite a bit of preparation, both formal and analytic. And in this lecture we're going to see how all that preparation pays off as we'll really get to the heart of analytic combinatorics, where we can derive asymptotic results directly from combinatorial constructions. We're at lecture 5, where we're finally at the point where we can do a specification, immediately get a generating function equation, and then immediately transfer to an asymptotic estimate of the coefficients. Now, the bottom line from the last lecture, you remember, we saw the light at the end of the tunnel. And with all the complex analysis that we prepared for, and Cauchy's theorem and residues and so forth, we wound up with this rather simple procedure that it turns out will be effective for a great many of the generating functions that arise from combinatorial constructions. So what we do is first find the smallest real pole that's smallest real pole, that's a root of the denominator of the meromorphic function. Then we calculate its residue just by evaluating the numerator at alpha and derivative of the denominator at alpha. Then our growth is a constant times beta to the n, where the constant is the residue divided by alpha, and the exponential growth, beta, is just 1 over alpha. So we're going to look at numerous applications of this simple procedure, and we don't need to look back at the residues and so forth where it came from. Although, as we'll see, it's sometimes interesting to really look at what the poles look like, and we'll talk about that somewhat. So let's start with the easiest example, Bitstrings. And this is just to warm up and get the format. Now we know that there's 2 to the n different bit strings of length n, and the generating function is going to be 1 over 1 minus 2z. From the standpoint of analytic combinatorics, we've seen many times the specification where a bit string is empty, or it's a 0 or 1 bit followed by a bit string, and that immediately translates to the generating function equation, 1 over 1 minus 2z. And now we could expand that directly to get 2 to the n, but let's look at what it looks like as a meromorphic function. There's a pole at alpha equals 1/2, and this is the plot of the magnitude plot of the function 1 over 1 minus 2z, and things get big at alpha equals 1/2. Then the residue, so the f of z in this case is 1, the g of z is 1 minus 2z, derivative of g of z is minus 2, the minuses cancel, the residue is 1/2. And so then the theorem says that our coefficient is those two things divided, which is just 1, and our exponential growth factor is 1 over alpha, which is 2 to the n. That's the analytic combinatorics methodology applied to this simple problem that admittedly we knew the answer to anyway, but as we've seen so many times, we can use the very same structure to do problems that we don't have the exact values of coefficients, and we can quickly derive asymptotic estimates of coefficients. So, for example, how many bit strings of length n have no 2 consecutive zeros? And there's ways to show that this one is the Fibonacci numbers, and we saw it before. But let's look at it again from analytic combinatorics. And we saw this construction in lecture 1. So class of all bit strings having no 0, 0 it's either empty, or it's a 0 bit, or a 0 bit followed by a bit string that starts with a 1 with no 0, 0, and so forth. And so that immediately translates to that generating function equation. That's a rational generating function. It's also meromorphic. This one has 2 poles. It's 1 minus, so one of the roots is phi hat square root of 5 minus 1 over 2, and the other one is minus phi, where that's the golden ratio. So 1 minus that times z, 1 minus that times z will give the result. And these things are related. Phi hat equals 1 over phi and so forth. Lots of calculations we're familiar with. But the residue is f evaluated at the pole closest to the origin, which is real, which is 1 plus phi hat. Derivative of g is 1 plus 2z, and minus that is minus 1 minus 2z, minus that is 1 plus 2z. Evaluated phi hat is that. And then a little bit of calculation, divide that by phi hat and do a little bit of calculation. We get the end result that the coefficient asymptotics of that is going to be close to golden ratio to the n times constant that we can calculate. So again, directly, just by finding the singularity, the closest root to the origin, then doing the calculations according to the normal procedure, we get the coefficient asymptotics. And this generalizes for this case, say we want to find the class Wall bit strings with no occurrence of 4 zeros in a row. The construction's easy. The translation down to the generating function just generalizes what we saw for the Fibonacci case. And now the singularity structure is a little more complicated. There's 4 poles, but only one of them's on the real line, and we're only interested in the one that's on the real line that's closest to the origin. So that's alpha, which we can calculate using a symbolic math system. Then we can go ahead and compute the residue, same as before, figure out what the coefficient is directly from the formula, and immediately with just a little bit of calculation, which again we can do with a symbolic math system, get a precise and accurate asymptotic formula for the coefficients. And remember, this is very accurate, that the terms we're forgetting about are exponentially smaller, and we'll see that in other examples. And it's just, this is just an interesting view of what the structure of the poles look like for this set of problems. So this is no 2 consecutive zeros that we saw. This is what 3 looks like. This is the one, 4 that we just saw. Here's 5, and you can see that we always have our dominant pole, which is on the real line and closer to the origin of any of the others. Remember from Pringside's theorem, that's going to happen for combinatorial generating functions like this. And then if you look at this is a big one with 10 consecutive zeros. Still, you can very quickly infer the structure, and we can know that when we get our asymptotic result for the coefficients, it's going to be very accurate because the contributions of these other terms are going to be exponentially smaller. They're much further away. So that's bit strings with restrictions on consecutive zeros. This generalizes, and this material is from part 1 of Analytic combinatorics, the next few slides. So I'll go quickly through it for people that have taken that course, and people that haven't taken that course, if you're confused by something on these slides, you might want to watch that lecture, which goes through more slowly and in more detail, but I'll go quickly through it now. Our generating function is the generating function for the number of bit strings that contain, say, no occurrence of m consecutive zeros. And then we went ahead and calculated what that looks like just using a combinatorial construction, and it turns out to have that form. That's just the generalization of the Fibonacci that we got for no 2 consecutive zeros. And actually, by multiplying by 1 minus z, both numerator and denominator, you get a slightly smaller form of that. That's the same function. Now, what's convenient about this particular generating function is if you evaluate it at z over 2, then it just divides by 2 to the n, and it turns it into a probability generating function. and evaluated at z equals 1. So, evaluated at z equals 1/2 is really what we're doing. So that gives some number of bit strings with no runs of m zeros divided by 2n. That's the probability that the first n bits of a bit string have no runs of m zeros. And we're summing those probabilities. That's the same as the probability that the end of the first bit string is bigger than n. And that gives the expected position of the end of the first occurrence of m zeros. Just evaluating the generating function at 1/2. So that immediately, just evaluating this at 1/2, immediately tells us that the probability that n bit string has no zero, and we know that, and if we just evaluate it at 1/2, we get 2 to the n plus 1 minus 2. So the expected position of the first run of m zeros in a random bit string is at 2 to the n plus 1 minus 2. And that's a simple probability calculation. And this is interesting to think about because if we go to different patterns that are not necessarily all zeros, we calculated the probability that a random bit string doesn't contain 4 zeros and showed that the expected wait time for 4 zeros is 30. What about for 001 or some other pattern? And what's interesting, if you haven't thought about it, is that it's not true. The wait time is different and probabilities are different. For example, 0001 occurs much earlier than 0000. And just to get a little intuition for that, just consider the first occurrence of 3 zeros in a row. So it's equally likely that 000 and 001 happen after that. But if the next bit is a 1, then you know you're going to have to wait 4 more bits to find 000. But if you're looking for 001 and the next bit is a 0, it could be that the next bit gives a match. So you ought to find 0001 sooner than 0000. That's just intuition. We'll show this analytically in just a minute. So we are interested in these problems, and there's lots of practical problems where we care about when patterns occur in random bit strings. So what is the probability that it doesn't contain 001 if it's not that? And what's the wait time for 0001? Well, generalizing the techniques that we used with generating functions, we can actually develop explicit formulas for these generating functions. And I'll just quickly go through this derivation again because it's from part 1, lecture 5. And what we do is we, for any pattern, say this pattern 10, 10, 0, 10, 10, we define 2 combinatorial classes, one for the strings that do not contain the pattern, and one for the class of strings that end in the pattern and have no other occurrence of it. And then what we do with that is we develop constructions, 2 different ways to construct these classes in terms of each other, and that gives us simultaneous equations that we can solve to get the generating function. So first one is, for example, to notice that these things are disjoint. If it doesn't contain P, then it can't end in P. That SP has the empty string, and if you add a bit to a string in SP, either you get a string that doesn't contain the pattern or you get a string that ends in the pattern. And that just corresponds to this combinatorial construction. The second construction is a little bit more complicated. It's developed in terms of what's called an autocorrelation polynomial, where we slide the pattern to itself, over to the left over itself, and if the trailing bits with the leading bits then we match, then we include a term. So 0 shift makes a match, but after a while, if we shift 5 positions, then 1010 matches the leading bits and so forth. So we define this thing in this way called the autocorrelation polynomial. And with the autocorrelation polynomial, we can develop another combinatorial construction, and I won't go through the details of this. Again, look in lecture 5 if you want to see them. That gives the construction of these 2 classes, SP and TP, in terms of the autocorrelation polynomial. So if we want to find the bit strings that don't contain a specified pattern, we have these two combinatorial classes. They have their generating functions, and we have the two constructions, and those constructions by the symbolic method immediately translate into two different generating function equations involving our generating functions of interest and the correlation polynomial. Solving those equations, then we get an explicit solution for a class of binary strings that do not contain a given pattern, a very simple rational generating function. So that's the ratio of two polynomials. And so that means that we can use the general procedure to go ahead and find that an asymptotic estimate for the coefficients just by plugging in, finding the dominant root of the polynomial that's closest to the origin, and then getting the explicit formula for the coefficient right from the basic procedure that we've used. It's two polynomials, we know how to deal with two polynomials. I'll leave a specific example of the analytic combinatorics going right from the spec down to asymptotics for an exercise at the end of this lecture. So that's an introduction to the use of the meromorphic transfer theorem as a part of analytic combinatorics to immediately derive asymptotic results for interesting practical combinatorial classes of interest, directly getting to accurate asymptotic results.